Okay, I see that some wind rustling sound is there in the previous podcast, but again, just to repeat myself, I do live without an AC, so here we go. The other thing we need to look at here before we go to the feedbacks is how the oceans play a role in climate variability, and the best way to start is to look at where all the additional energy that's being trapped by human activities, global warming, is going. And this is a nice figure. This is from Skeptical Science, which I should have put here, but such a figure is provided by many, including, I think, Wikipedia. So ocean takes up 93.4% of all the energy. Atmosphere has a low heat capacity, so only keeps 2.3%, which means the warming that we keep talking about is heavily reduced by the energy that is being stored in the ocean. It's not gone out of the system, it's just there, and ocean can release it at several times, at many different time scales. Ocean is deep, has a very high heat capacity, is very dense compared to the atmosphere, and has a long memory, so it provides most of the memory for low frequency variability. Continents keep a tiny bit, they also have a low heat capacity. Glaciers and ice caps obviously are a store, because the additional energy is going into melting glaciers. Arctic ice has a 0.8%, Greenland ice sheet 0.2%, Antarctic ice sheet 0.2%. Obviously there are some uncertainties in these numbers, but one thing that doesn't change is ocean absorbs more than 90% of the additional energy. And this is relevant at all time scales. So if you look at land elevation and ocean depth showing continental shelves of the world and indicating location of the Bering Strait continental shelf, during Beringia, we talked about the land bridge and the migration pathways for the Clovis, for example, whether you took the coastal path or they went interior around open areas in glaciers and spread inside, and how they crossed the central America into South America, and so on and so forth. So over time, glaciation has changed these pathways, of course, and these that we talked about before in terms of sea level changes. We talked about closing of the Isthmus of Panama, opening of the Drake Passage, and so on. So oceans have played a role in many ways, other than the fact that they remain a huge storage of energy. So you can imagine sun stays in one hemisphere for 6 months and another hemisphere for 6 months. During the whole time, ocean is taking up energy and it's moving it around and releasing it at various time scales. So weather, day-to-day changes for a few days are almost entirely determined by the atmosphere, because it can run around and do what it wants. But if it wants to change on a slower time scale, it has to rely on the ocean. So ocean begins to control seasonal variabilities, multiple weeks and decades and centuries and longer. How does it do that? There is something called deep water, the Thermohaline Circulation. So winds obviously drag the ocean around, and sea surface temperatures change on various time scales that are much faster than the deeper part of the ocean, which is moving very slowly and isn't exchanging heat very quickly with the atmosphere. Near the surface, wind forcing and exchanges of heat with the atmosphere can make a huge difference, especially the evaporation that we talked about. But deeper ocean is set in motion by the so-called thermohaline circulation. There are special places, like in the North Atlantic off of Greenland, Iceland, Norwegian seas, where conditions are created for dense water to form and sink, which means new water has to come in and replace it. So you can see the blue colors here are deeper parts of the circulation, way below the surface, 1 to 2 kilometers or deeper, and the surface circulation that is supplying those sinking regions just for continuity purposes and so on. So that is the Atlantic meridional overturning circulation. Meridional is, of course, in the latitudinal sense. That water comes into the Southern Ocean, which is a channel, and there are a couple of spots where very heavy water forms in the Antarctic as well, in the Ross Sea, Weddell Sea, and so on. And those waters circulate around, get mixed up together. It's like a mixing bowl, and those waters then inundate the Indian Ocean, which is closed off to the north at a low latitude, and the Pacific Ocean, which goes all the way to the Bering Strait, as we just saw. So that those waters that are shown in blue here take here maybe very quickly in multiple decades, get converted back to surface water, come back, go around the South African coast here and go back to the north in the Atlantic. In the Pacific, they come up, become surface waters over hundreds to thousands of years and cross into the Atlantic through the so-called Indonesian through-flow pathway, Indonesian seas, and those are the pathways that changed in the past. So the waters are circulating here, forming deep waters forming here and here, circulating in the Southern Ocean, inundating the Indian Ocean and coming back out, inundating the Pacific Ocean and coming back out, and that water is crossing in here, merging with the Indian Ocean water and going back out, or some of it is going back eastward, and so on and so forth. So this is the so-called thermohaline circulation. We will use many isotopes like carbon-14, delta O18, O16 ratios, and C13 and C12 ratios, and so on, to understand various things like how old is the water in the North Pacific, right? That's the farthest point from the deep water formation sites. How long does the water take to go out and convert it back to surface waters and come back, and so on and so forth. So we use the so-called Paleo Proxies to figure those things out. Proxies because they give you an indication of past temperature changes, but they are not direct temperature measurements. They are proxies for temperature changes, because many things that are formed in the ocean, or things like glaciers that lock up the water, leave signatures, biogeochemical signatures that are either in the ice cores, in glaciers, in ocean sediments, lake sediments, and even tree rings and corals, and so on and so forth. So we'll have a brief introduction to proxies in a bit, but before that we will look at the podcast. So the main thing to remember is that the ocean has played a big role and continues to play a big role in modulating climate variability and climate change. Okay, what do you mean by change? When we look at time scales where change goes in one direction, like warming or cooling, as opposed to going up and down, we call it change. How long should it change before we call it change? Well, there is no strict definition. This is why we end up with things like interannual variability, where things change from year to year, like El Nino and La Nina. If you don't know what they are, you can look up my other podcasts. We have things like decadal variability, where things change from one decade to the next or multiple decades, like the so-called Atlantic multi-decadal oscillation, which we may come back to a little bit later on, or the Pacific decadal oscillation. These are patterns of observed temperature changes, associated changes in rainfall patterns, and so on and so forth. And you also have centennial time scales and longer time scales, because ocean can generate all these kinds of low frequencies because of this thermohaline circulation, and so on, and of course because glaciers can form and melt because of orbital forcing as well. And anthropogenic change now is the word we use, where since the Industrial Revolution we have been pushing up the greenhouse gas concentrations in the atmosphere. So we are changing the energy balance now on this human time scale, let's say of a century or two. We'll continue to do that for some time, of course. So this is man-made changes in energy balance and resulting temperature changes, glacier changes, land changes, vegetation changes are called anthropogenic changes. So in the past, things have changed, and we will look at 135,000 year time chunk, especially because that's where most of the human migrations, human evolutions, behavioral changes, developmental changes, anatomical changes, and so on happened. And the other species have also evolved, C3, C4, and all the other megafaunal changes we have seen. So ocean is again very critical for all these time scales that we are talking about, because all the low frequencies come from ocean memory, and of course glaciers as well that can lock up water and heat in terms of evaporated ocean water falling as snow and being locked up. And to melt those glaciers, we need to provide the energy back. So these are the things we will look at with key concepts. But once you start these changes, there are feedbacks in the system. So in the next podcast, we will look at the feedbacks in the Earth system that are critical, and the various time scales at which those feedbacks work. There are many figures of feedbacks you will find. I will use a particular set of figures, but the ideas are still the same. So just make sure you understand what we mean by feedback. So we'll define those and look at those in a minute. Okay.